Two countries, a stretch of open sea between them, and a problem that defeated every engineer who tried to solve it for 40 years. You cannot build a bridge. The seabed is too soft. You cannot drill a tunnel. The boulders will destroy the machine. So how do you cross? The answer is sitting in a factory in Denmark right now. 89 of them, each one the size of a skyscraper, each one about to become part of the floor of the Baltic Sea. This is the Fehmarn Belt Tunnel, the most complex immersed tunnel ever built. A bridge across the Fehmarn Belt looked inevitable. Towers taller than city skyscrapers, steel cables stretching across the open sea, a structure to rival anything in Europe. But the seabed had other plans. Beneath the waves, a layer of soft marine clay, 30 meters thick, waited, silent and unforgiving. Engineers drilled 46 boreholes down to 40 meters, each core sample telling the same story. The clay was too weak, too compressible. Every foundation design, piles, caissons, even suction buckets, was tested against the numbers. The main bridge towers would each load the seabed with 80,000 kilonewtons, spread across a 300 square meter pile cap. That is a bearing pressure of 267 kilopascals. Safe on paper, but the real threat was not pressure, it was movement. Settlement calculations ran through finite element models. The numbers came back 120 millimeters of total settlement in just 5 years. That is 4 times the maximum allowed. Differential settlement, how much one tower would sink compared to its neighbor, reached 140 millimeters. The limit was 30. Each tower might tilt by 1/4 of a degree. The design could only tolerate 0.3 degrees. There was no margin for error, no room for storms, for earthquakes, for the slow creep of clay under decades of weight. A senior geotechnical lead stood before the project steering committee with the results. Compression index, 0.34, shear strength, barely enough in pockets, dangerously low in others. Even the most massive caisson, 30 meters deep and 5 meters thick, would sink 70 millimeters in the worst spot. To hold the tower steady, engineers would need over 500 piles per tower, driving costs up by more than 1 billion euros. The risk of catastrophic tilt or cable misalignment could not be engineered away. The verdict was unanimous. The bridge plan was dead. Regulatory documents from 2019 made it official. The Fehmarn Belt's soft clay made a fixed bridge impossible. The only way forward would be underground. But the ground, as it turned out, had more surprises in store. A tunnel boring machine the size of a city block waits on the Danish shore. Engineers call it Mastodon. The plan is to drive this mechanical giant under the Fehmarn Belt, carving an 18-kilometer path through the earth. But the geology is not just soft clay, it is a minefield. Glacial boulders, some over 2 meters across, lie hidden in the till. Each one is a silent threat. Seismic surveys and borehole cores map the danger, but the data is incomplete. Ground-penetrating radar cannot see through the dense marine clay. The hazard map lights up with warning. In the central corridor, there is a 30% chance of hitting a boulder bigger than the cutter head can survive every 100 meters. The TBM's shielded face, armored with steel and tungsten, is rated for rocks up to 2 meters. But the risk models show erratics as large as 6 meters, scattered at random depths. The cutter head cannot shear them. It cannot even push them aside. One direct collision, and the entire machine could be immobilized, stuck beneath the sea, a 350 million euros loss. Recovery would mean months of downtime, a heavy lift vessel, and the real possibility of never retrieving the machine at all. A risk manager for the TBM project stands before the steering committee. He does not sugarcoat the numbers. Monte Carlo simulations, 10,000 runs, all point to the same conclusion. More than a 1 in 3 chance of catastrophic failure, before reaching the German shore. The mean downtime for a stuck cutter head is 120 days. A breached pressure chamber could flood the tunnel, trapping the TBM permanently. The cost is 18 months of schedule lost, a 12% spike in total project cost, and a public relations disaster. No amount of pre-drilling or rerouting can guarantee a safe corridor. The Channel Tunnel and Tokyo Bay projects survived with luck and costly interventions, but their boulder risk was a fraction of what the Fehmarn Belt presents. Here, the density of erratics and the length of the tunnel make mitigation impossible at scale. The verdict is unanimous. The TBM option is dead. The tunnel cannot be bored. The seabed has defeated both the bridge and the machine. The committee turns to the last option left: build the tunnel on land and then sink it beneath the sea. At Rodbyhaven, the solution takes shape not in the water, but on dry land. Here, the tunnel is not bored or built in place, it is manufactured. 89 colossal elements, each weighing 73,000 tons, each one longer than 2 football fields, as tall as a 6-story building, and packed with enough steel to build a fleet of freight trains. The factory runs around the clock. Concrete never stops flowing. Pouring one of these giants is not a matter of hours or even a single day. It takes 72 hours, non-stop, no breaks. Once the pour begins, the concrete must keep moving, layer after layer, until the form is full. Temperature sensors are embedded every 5 meters, tracking the heat as the cement cures. Too hot and cracks form, too cold and the structure weakens. Chilled water jackets snake through the formwork, pulling excess heat away, keeping the chemical reaction in check. Every element is a fortress of rebar. Over 2,000 tons of high-strength steel are bent and welded into a dense, 3-dimensional cage. Robotic arms handle the heaviest bars, but every weld is checked by hand and scanned by ultrasonic testers. Placement tolerances are tight, plus or minus 5 millimeters over a 200-meter span. The inspection team walks the length, checking, logging, signing off. Nothing moves forward until every metric is verified. After curing, each element is pressure tested. Flooded with water, pressurized to simulate 40 meters of Baltic Sea above, every joint, seam, and gasket seat is checked for leaks. Laser trackers scan the surface, confirming the dimensions down to the millimeter. Only when the digital twin matches the physical giant does the element earn its place in the queue. Then, and only then, is it rolled out of the casting hall, ready for the next phase, the journey to the sea. A 73,000-ton tunnel section inches across the harbor, buoyant but barely afloat. Tugboats swarm around it, their engines straining, cables tight as piano wire. The tugmaster, eyes locked on the GPS RTK readout, calls out corrections. Every movement is tracked to within 10 centimeters. Acoustic transponders ping from the seabed, guiding the convoy over a trench 40 meters deep. There is no second chance. One bad gust, one miscalculated current, and the element could swing, collide, or even founder. At the target, the descent begins. Ballast tanks flood in a precise sequence, water rushing in by the ton. The element sinks, meter by meter, its trim and pitch adjusted by remote valves. Deck tanks first, then side tanks, each step checked against the digital model. The margin for error narrows to 5 centimeters. On the seabed, a gravel cushion waits, engineered to cradle the concrete without a single point load. Hydraulic jacks engage, pushing the new section toward its neighbor. Now comes the moment of truth. The Gina gasket, a 30-centimeter thick ring of EPDM rubber, must compress perfectly to form a watertight seal. The pressure outside is relentless, 4 bar, enough to flatten a car tire 4 times over. Sensors monitor the gasket as it deforms, measuring every micron, leak-free at design pressure, no alarms. But the final connection is not left to machines. In a habitat pressurized for a month-long stay, a saturation diver prepares for his shift. He moves through cold green water, tools clipped to his harness, helmet lights cutting the murk. At 40 meters down, he inspects the joint by hand, feeling for irregularities, confirming the seal. He injects grout, checks the pressure, signs off on the joint. 28 days in a steel capsule, all for a few hours of work that decide whether the tunnel stays dry. The diver's job is the last defense against the Baltic. When he surfaces, the crossing has a new, permanent link, one more victory over the sea and the clay below. Today, a tunnel longer than 110 skyscrapers end-to-end cuts beneath the Baltic Sea, defying soft clay and buried boulders. Every train and truck racing through proves this. When nature sets the rules, reinvention is the only way forward. Sometimes, to cross the impossible, you have to sink it.